Welcome back to Explained. You know, where we take those complex topics and make them well explained. And today, we're going deep into the invisible world, that powers our internet experience. Like, imagine sending a message across the globe just like that, in the blink of an eye. How does it actually get there reliably?
Yeah, it's like magic, right?
It is what keeps everything running smoothly behind the scenes.
Right.
Well, that's what we're diving into today. The often overlooked transport layer.
Yes.
And its two key players, TCP and UDP.
Mm-hmm.
Now, have you ever stopped to think about what happens when you send an email or watch a video online? Let us know your thoughts in the comments.
It's amazing how we take these processes for granted, right?
Yeah, we do.
I mean, they're the unsung heroes of our digital lives working tirelessly behind the scenes to ensure our data gets where it needs to go. The transport layer acts like a sophisticated postal service, ensuring those tiny bits of information called packets reach their destination in the right order without any damage along the way.
So TCP and UDP are the two main delivery methods in this postal service.
Exactly.
But they have very different approaches to the task.
Yeah. TCP, or Transmission Control Protocol, is like sending a certified letter with a return receipt. It guarantees that your data will arrive at its destination and that the recipient will acknowledge receipt.
Oh.
This makes it perfect for applications where data integrity is crucial, like when you're sending important documents or browsing the web.
Right. That makes perfect sense for things like email or online banking, where accuracy is paramount. But wouldn't all that checking and confirming slow things down? What about situations where speed is more important than absolute certainty?
That's where UDP comes in, User Datagram Protocol. Think of it like sending a postcard. It's fast, lightweight, and gets the message across quickly, but without the guarantee of delivery or the need for a confirmation.
So if a few postcards get lost along the way, it's not the end of the world.
Exactly. UDP is all about speed and efficiency. It's perfect for things like live video streaming or online gaming, where a slight delay is far more noticeable than the occasional dropped packet.
Okay, so we have the reliable letter sender, TCP, and the speedy postcard enthusiast, UDP. But how do they actually work in practice? Can you give us some real-world examples?
Sure. Let's say you're browsing the web. Your browser uses TCP to establish connection with the web server, ensuring that all the data needed to load the web page arrives correctly and in the right order. It's like a carefully choreographed handshake before a formal meeting.
Okay, so TCP is all about setting up a secure and reliable channel before any actual data is exchanged.
Precisely. And this reliability comes at a cost. TCP involves a lot of back-and-forth communication to make sure everything is in order, which can add a bit of overhead. That's why UDP shines in situations where speed is paramount, like a live video call. You want the conversation to flow smoothly, even if a few words get lost along the way.
This is starting to make a lot of sense. But here's a question that's been bugging me. How do multiple applications on my computer share the same internet connection? It's not like each app has its own dedicated cable running to the outside world, right?
That's a great question. It all comes down to a clever mechanism called multiplexing and demultiplexing. Imagine an apartment building with one main entrance. Multiplexing is like having an intelligent doorman who can direct incoming packets to the correct apartment, or in this case, the correct application.
So it's like a traffic management system within our own devices.
Exactly. Each application is assigned a unique port number, which acts like an apartment number within your computer's network address. This ensures that incoming data is delivered to the right application, even if multiple applications are using the internet connection simultaneously.
That's amazing. It's like a well-oiled machine working behind the scenes to keep everything running smoothly. Now let's dive a bit deeper into how TCP ensures the reliable delivery of data. Let's say I'm sending a large file to a friend. How does TCP make sure they receive it without any data getting lost or jumbled?
TCP has a brilliant system of sequence numbers and acknowledgements. Imagine each packet being numbered. The receiver confirms receipt by sending back an acknowledgement with the next expected sequence number. If a packet goes missing or arrives out of order, the receiver can request a retransmission.
Oh, so it's like a self-correcting system, constantly checking and adjusting to make sure everything arrives in perfect condition.
Exactly. It's like having a meticulous librarian who insists on putting every book back in its proper place on the shelf. This attention to detail is what makes TCP so reliable, but it also adds some overhead to the process.
Now, I'm curious about the other side of the coin. What happens when my internet connection is slow, and I'm trying to download a large file from a server with a super fast connection? Wouldn't that cause problems?
You're right, that could lead to data overload. That's where flow control comes in. It's like a pressure valve that prevents a fast sender from overwhelming a slow receiver.
So it's all about finding the right balance of data flow to ensure a smooth transfer.
Exactly. The receiver communicates its available buffer space. Think of it as the amount of data it can comfortably handle at a given time. And the sender adjusts its sending rate accordingly.
That's a clever way to prevent things from getting backed up. But what about the bigger picture? What happens when the entire network gets congested, like during peak hours when everyone is online?
That's when things get really interesting. That's where TCP's congestion control mechanisms come into play. Think of it like a traffic management system for the entire internet designed to keep things flowing smoothly even when things get crowded.
I'm starting to see how complex this all is. Don't forget to follow Explained for more deep dives into the incredible world of technology. Now, I'm curious what happens when even UDP's speed isn't enough. Is there anything faster?
That's a fantastic question and leads us to the evolution of the transport layer. While TCP and UDP have been the workhorses for decades, new challenges have emerged with the rise of demanding applications like high-definition video streaming and online gaming.
So are TCP and UDP starting to show their age? Are they up to the task of handling these new demands?
That's a great question. TCP, with its reliability and congestion control, is still a workhorse for many applications. But its complexity can sometimes lead to overhead and delays, especially in high-speed networks. UDP is fantastic for speed and efficiency, but its lack of reliability can be a deal breaker for some applications.
So it sounds like we need something that combines the best of both worlds. Is that even possible?
Actually, yes, and that's where a newer protocol called QUIC comes into play. QUIC, or QUIC UDP Internet Connections. It's a relatively new protocol that builds upon the strengths of UDP while adding some of the reliability features of TCP.
So it's like a souped-up version of UDP.
Exactly. It aims to provide the speed and efficiency of UDP without sacrificing the reliability that's crucial for many applications. One of the key innovations of QUIC is that it moves some of the functionalities traditionally handled by TCP into the application layer. This allows for greater flexibility and customization, tailoring the protocol to specific application needs.
So it's like giving applications more control over how their data is transported.
Precisely. This can lead to significant performance improvements. For example, QUIC uses a streamlined connection establishment process, reducing the initial handshake time needed before data transfer can begin. This is especially beneficial for mobile networks where connections can be unstable.
Wow, that's impressive. So QUIC sounds like it's poised to be a major player in the future of internet communication. But before we get ahead of ourselves, let's take a closer look at UDP. It might be the simpler protocol, but it's still got a lot going on under the hood.
You're absolutely right. Let's break down the anatomy of a UDP segment and understand how it manages to be so lightweight yet effective for certain applications.
Okay, I'm ready to decode those UDP packets. Listeners, stay tuned as we break down the anatomy of UDP, and remember to hit that subscribe button so you don't miss our next episode, where we'll be exploring even more fascinating tech topics.
A UDP segment, which is essentially a UDP data packet, is like a minimalist package. It has just 4 main parts: the source port number, the destination port number, the length of the data, and a checksum.
Okay, so it's like an address label with some basic information about the contents.
Yeah.
But what's this checksum thing? It sounds like some kind of security measure.
You got it. The checksum is a simple yet powerful error detection mechanism. It's like a mathematical fingerprint of the data. The sender calculates this checksum and includes it in the segment. When the receiver gets the segment, it recalculates the checksum. If the 2 checksums match, it's a good indication that the data arrived intact.
So it's like a quick check to make sure nothing got messed up in transit.
Yeah.
What if the checksums don't match?
If the checksums don't match, the receiver knows that something went wrong along the way, and it simply discards the corrupted segment. There's no retransmission mechanism in UDP, unlike TCP.
Ah, that explains why UDP is faster, but less reliable. It's trading some accuracy for speed.
Precisely. And this trade-off makes UDP perfect for applications where occasional data loss is acceptable, like streaming live video. A few missing packets might cause a slight glitch, but it's better than the stream freezing up while waiting for retransmissions.
That makes a lot of sense.
Yeah.
Now, I'm curious about something. We've talked about how TCP handles congestion when the network gets crowded. But does UDP have any mechanisms to deal with congestion?
That's a great question. Unlike TCP, UDP itself doesn't have any built-in congestion control mechanisms. It relies on the applications using it to implement their own strategies for dealing with network congestion. This might involve things like adjusting the sending rate or using buffering techniques to smooth out the data flow.
So it's up to the applications to play nice and avoid overwhelming the network.
Exactly. While this might seem like a recipe for chaos, it actually gives developers more flexibility to optimize their applications for specific needs. For example, a video streaming application might prioritize sending the most important data, even if it means dropping some less critical packets during periods of congestion.
That's a fascinating insight. It seems like there's always a trade-off between speed, reliability, and complexity in the world of networking protocols. Now, I'm curious, are there any other exciting developments in the world of transport protocols? What does the future hold for this crucial layer of the internet?
That's where things get really interesting. While TCP, UDP, and QUIC are the dominant protocols today, the internet is constantly evolving and new challenges are emerging. For example, think about the massive amounts of data being transferred in today's cloud-based world, or the need for ultra-low latency in online gaming. Researchers are constantly exploring new ideas and approaches to improve the performance and efficiency of the transport layer.
So it sounds like the future of the internet is going to be even faster, more efficient, and more interconnected than ever before.
Absolutely. And as we move towards a world of interconnected devices, the role of the transport layer will become even more critical.
This is incredibly exciting. It's amazing to see how the humble beginnings of TCP and UDP have led to such innovative advancements in the world of networking. But before we wrap up this episode, let's take a quick step back and recap the key differences between TCP and UDP. It's important to remember that both protocols have their strengths and weaknesses, making them suitable for different types of applications.
Absolutely. Let's highlight those key differences so our listeners can fully grasp the nuances of these essential internet protocols.
Great idea. So listeners, get ready for a quick showdown between the titans of the transport layer TCP versus UDP. All right, it's time for the ultimate showdown, TCP versus UDP. Let's start with TCP. So give us the lowdown on what makes TCP so reliable.
Well, TCP is like a meticulous courier service. It ensures your data package arrives at its destination safely and in perfect condition. It uses a system of acknowledgments and retransmissions to guarantee delivery. It's like sending a package with trapping and insurance. You know it will get there.
Yeah.
And you can rest assured that it hasn't been tampered with along the way.
So TCP is the go-to choice for applications where data integrity is paramount. But what about those times when speed trumps reliability? That's where UDP steps in, right?
Precisely. UDP is more like sending a letter via airmail. It's fast and lightweight, but there's no guarantee that it will arrive or that it won't get crumpled along the way. It's a trade-off speed for a bit of risk. But for applications like streaming video or online gaming where a few dropped packets won't ruin the experience, UDP's speed and efficiency make it the ideal choice.
So it's all about choosing the right tool for the job. TCP for reliability, UDP for speed, but let's not forget about QUIC, the up-and-coming protocol that aims to combine the best of both worlds. So remind us, what makes QUIC so special?
QUIC is like a high-speed train. It's built for speed, but it also has safety features like a robust track system and signaling to prevent collisions. It takes the speed and efficiency of UDP and adds some of the reliability features of TCP, like congestion control and error correction.
So QUIC is like having your cake and eating it too. You get the speed of UDP without sacrificing the reliability of TCP. It sounds like a game changer.
It certainly has the potential to be. QUIC is already being adopted by major companies like Google and Facebook to improve the performance of their services. And as the demand for faster, more efficient internet experiences continues to grow, QUIC is poised to play an even bigger role in the future of the internet.
Now, can you think of any other applications that would benefit from either TCP or UDP? What about QUIC? Share your thoughts in the comments below. This deep dive has been a fascinating journey into the hidden world of internet protocols. We've explored the strengths and weaknesses of TCP and UDP, and we've seen how QUIC is pushing the boundaries of internet speed and reliability. Don't forget to follow Explained for more insightful deep dives into a variety of topics. If you have any suggestions for topics you'd like us to explore, be sure to let us know. We're always on the lookout for new and exciting subjects to unravel. Thanks for joining us on this incredible journey into the heart of the internet.